Welcome everybody to another webinar in our series Lunch with the NMSP, Food for Thought. Today's webinar number 7, and we're going to be talking about sulfur. I want to get started with a quick introduction for those of you that might be less familiar with our program. My name is Colleen Kettlings. I lead the Nutrient Management Spear program here at Cornell University. We are the designated program for the land grant mission for New York to supply farmers with guidance, science-based guidance for nutrient management of field crops. Our motto is relevant questions and sound science for agriculture, profitability, and protection of the environment. And our main goal is to help our agricultural sector improve profitability and competitiveness of New York dairy, livestock, and cash grain operations while maximizing environmental protection. We have 6 focal areas in our program. The first one is that land grant responsibility to develop, implement, and support those science-based guidance for nutrient management. We also work on soil health and climate resiliency. We have a precision ag component in our program, dairy sustainability, assessment tools, assessments at the whole farm level. We have an on-farm research program, and we have a focal area in terms of student engagement, evolving the next generation to help us solve agricultural challenges. Today's webinar is a component out of our land grant responsibility. We'll be talking about sulfur, but also share some of our on-farm research results on sulfur management with you all. We are celebrating 25 years of our program. Last August 1st was 25 years, so we're in our next year now. And we decided to add to our plate to do this webinar series once a month, 1 hour over the lunchtime hour. We've done 6 of those webinars so far. The series is posted here. If you happen to have missed one, you want to go back to one, all of our past webinars are now posted on our Animal Science YouTube channel. So you can find the webinars there in full. And the one for today will be posted there next week as well. Our next webinar is on potassium management with the question, when is too much indeed more than we need? And we can turn it around as well. When do we know that we need to add more potash to get the crop yields and crop quality that we're shooting for? Our webinar series is designed to be on the first Friday of every month. We just learned yesterday that July 3rd is apparently a holiday for Cornell. So I have to move the webinar series. I'll be doing that a week later, July 10th. So potassium management, next webinar in July is not on the first Friday, but the second Friday in the month. Let's dive into our webinar for today. So I'll be presenting here, but I'll be presenting work that is done by a much larger group. That includes the folks listed here on the screen that have worked in past research projects and laboratory projects, getting information together. A couple of degree programs involved here too. So I want to thank everybody that has participated to building the guidance that we will be talking about. Some of the research that we will be talking about here today in the webinar, including the participating farms that worked with us on the various projects and our own team members within the NMSP. Made an outline here, talk a little bit about the importance of sulfur, uptake by uptake numbers, what kind of numbers are we talking about, the sulfur cycle, and then how we can identify if we have deficiencies. Then if we know that we have a deficiency, the next question is how do we take care of that? So we'll talk a little bit about fertilizers, sulfur containing fertilizers and manure and sulfur. And I'll share some assessment studies with both alfalfa and with soybeans to illustrate whether or not we have deficiencies in New York before we wrap this up. Let's start with the importance of sulfur. We know crops need certain things to grow and produce. That includes oxygen, water, light. We need some nice temperatures, some structural support that crops can root into, some carbon. And the webinar of last month was all about pH, so we also know pH is really important for management of crops. The focus today, though, is on the nutrient side of things. And particularly, when we talk about nutrients, we need to recognize that we have 17 essential nutrients for plant growth. They're all listed on the screen here. They are divided into three main groups: structural nutrients, primary macronutrients, and micronutrients. The structural nutrients, that's carbon, hydrogen, oxygen. The primary macronutrients and the secondary macronutrients are nitrogen, phosphorus, and potassium for primary, and calcium, magnesium, and sulfur for secondary. And then the micronutrients are listed here: boron, copper, iron, manganese, zinc, molybdenum, chloride, and nickel. All 17 are essential. If any of those are lacking, we have an issue. The difference here between macro and micro is in the amount needed, so the total pounds that we need to supply to the crop, or the total pounds that the crop will take up. Micronutrients are taken up in small quantities. Macronutrients are taken up in much larger quantities. And the division between primary and secondary has nothing to do with their importance. It simply is division between primary are the nutrients taken up in larger quantities than the secondary macronutrients that are taken up in somewhat smaller quantities than the primary. So all of them are essential. We'll talk about other nutrients as we go along in the webinar series in the future as well. Today, we're going to focus entirely on sulfur. So, importance of sulfur. It is an important component of numerous protein enzymes that regulate two really important processes for plant production: photosynthesis, that is important for all plants, and nitrogen fixation, that is important for our legume crops, soybeans, alfalfa. Sulfur deficiency, so if there's not enough, can lead to lower crop yields. Deficiencies include proteins, so uptake of nitrogen, fixation of nitrogen, reduced milk production, decreases in overall feed efficiencies on the dairy farms that we're trying to support with these crops. So sulfur is really important. Major processes within the plant that are impacted if we have sulfur deficiencies. And it doesn't matter if it's a legume or a non-legume, photosynthesis is important for both. So we need to watch our sulfur management for both our corn crops as well as our soybean and alfalfa crops. So what kind of numbers are we talking about in terms of uptake? One way to do this and to approach getting some estimates is to look at databases with average nutrient contents, look for its quality analysis that laboratories might be doing. Here's a bunch of new numbers that I got from the Forage database of Dairy One, with using the averages of the ranges they reported for these different crops. And I have corn silage, corn grain, alfalfa, grass, and soybeans here. The S removal is basically in the S content per unit of crop produced. So a little less than 5 pounds of sulfur per ton of alfalfa hay at 90% dry matter, or 1.7 pounds of sulfur per ton of silage, alfalfa silage at 35% dry matter. With these numbers, we can do conversions, and when we combine this with yields, we can come up with crop removal numbers. And that's what this shows. So we have corn silage, the first two. We'll go with that example first. Corn silage, tons per acre. If your harvest for corn silage at 35% dry matter is, let's say, 20 tons per acre, your estimated crop removal based on these book values, these averages, is 14 pounds of sulfur per acre. If you have a bump-up crop and you have 35 tons of corn silage at 35% dry matter, your crop removal would be 24 pounds of sulfur on average. Corn grain, we see somewhat lower numbers. That's because we only remove the grain and not the whole plant. And a crop of 170 bushel would give us a crop removal of about 8 pounds of sulfur. Alfalfa, 3 tons of pure dry matter would give us about 15 pounds of sulfur. If we have a bumper crop and we get 6 tons, it would give us a crop removal of about 29, almost 30 pounds of sulfur per acre. Soybeans, 50 bushel equates to about 8 pounds. We get 70 bushel, 11 pounds, 80 bushel, 13 pounds. The things that we can see in this table is that sulfur removal is typically less than 15 pounds of sulfur per acre, but it could be up to 30 pounds in high yielding fields, particularly when we deal with a crop like alfalfa. And the plants that we move entirely, alfalfa harvest or corn silage harvest, have larger numbers than corn grain and soybean when we only remove the grain. All right. The biggest sulfur removal in our crop rotation systems here in New York would be alfalfa. Let's take a look at how do we get sulfur to our crops. This is a schematic of the sulfur cycle. And those of you familiar with the nitrogen cycle will recognize there's a lot of similarity here. We look at sulfur and plant uptake. Sulfur is taken up from soil solution primarily as sulfate in soil solution, similar to nitrate in soil solution for nitrogen. Sulfate is subject to leaching, just like nitrate is, so it can be lost from our system through leaching. It can also be supplied to the soil through mineralization of organic matter or organic resources that might be added to the field, manure, crop residues, cover cropping. These can all add organic matter to the soil. When it mineralizes, that can become sulfate in solution and be taken up by crops. Sulfur can be lost through volatilization to the air. And on the other side, sulfur that's in the air can be deposited back to a land base. Typically not in the same place that it's lost from, but it can be deposited back as sulfur deposition from the air. Now, in the past, and I'm talking about 25, 30 years ago, this component here, the sulfur deposition, was a major contributor to plant uptake and sulfur supply. Let's take a look. This is a map from US EPA, total deposition map for sulfur. The legend here is in kilograms per hectare. That is just a tiny little bit bigger than pounds per acre, but for all practical purposes, consider that to be very close. This was the map in 2000. Total deposition of sulfur, that's wet and dry deposition together, sulfur in 2000. And zoom in on New York and take a look. It's going to change. We're going from 2000 to 2024. Here we go. On 2010. To 2024. Back to 2000. Basically, what we see here is that the areas with substantial deposition back in 2000, through the cleaning of our smokestacks, have now gone to very low sulfur deposition numbers. If we compare the two maps, 2000 and 2024, you see the drastic difference there in numbers. Went back a little bit further also with some records that I was able to track down in New York. Deposition changed from back in the mid-80s when my predecessor was doing sulfur trials and concluded we had no sulfur deficiencies in New York State, with a 14 pound of sulfur deposition, to now less than 4 pounds of sulfur per acre coming through deposition from wet or dry deposition. A drastic change. My predecessor did field trials back in the 80s, found no response to sulfur for those trials. What is the situation now? We'll take a look. So, sulfur cycle, this major contribution, 14 pounds for New York on average in 2000. is now reduced to less than 4 pounds. Remember the crop uptake for most of our crops? We're talking about 15 pounds of sulfur, maybe up to 30 for a high yielding field. Losing this amount of sulfur means that we need to rely more on the soil supply of that sulfur, or we need to start adding sulfur in terms of fertilizer additions. All right, so how do we identify if we have a deficiency? Let's take a look first at what it looks like. Here's 3 pictures. We go on the left with corn, in the middle with alfalfa, on the right we have soybean, all images of sulfur deficiencies. And while it might look striking in some scenarios, particularly for corn, it's not always easy to identify visually. The other thing is, by the time you identify it visually, you already have suffered a yield hit because of lack of sulfur. But this is what it would look like. One major thing to remember, sulfur deficiency can be confused with nitrogen deficiencies, is that sulfur is not so mobile in the plant. So the deficiencies show up in the newest leaves, the youngest leaves, the top of the plant, versus nitrogen that shows up at the bottom of the plant, because nitrogen is mobile in the plant and the younger leaves can grab it from the older leaves. For sulfur, that cannot happen. So the deficiencies are shown in the younger growth of our crops. Tissue testing has been around for quite a while and promoted to identify some of these deficiencies. In terms of sulfur, there's 2 things that we have to watch, and that is the interpretations themselves that vary from crop to crop, from stage to stage. So it is important to know the protocol for sampling to be able to interpret the results that you get back from a laboratory. In this slide, you see on the left when to sample. There's a couple of options for each of these crops. Alfalfa is early bloom. What to sample, top 6 inches. And then it gives a recommendation for the number of plants that you might want to combine for sending to a laboratory for testing. Corn, there's 3 stages of sampling. Soybean, same thing. Prior to flower, early bloom, prior to pod set. All 3 stages. You want to collect from the most recently developed trifoliate, and then again a number of plants. The interpretations on the right, for alfalfa, if you follow that protocol of top 6 inches at early bloom, the range here suggests an optimum range. If it's less than 0.25%, it could signal that we have a sulfur deficiency. If it's 0.25% or greater, no concern. So it's really important to know what the protocol is for testing and to follow that, because otherwise it's difficult to compare the ranges that are posted with your results. To show how important that protocol is, here's a slide from Jerry Cherney in Soil and Crop Sciences at Cornell, where he did section sampling on plants, alfalfa plants. He took the top 6 inches, as the protocol says, and then he took the next 6 inches and the next 6 inches going down to the ground. If we zoom in on the purplish location, so this is for 3 locations, let's take a look at location 1. If we took the right protocol, it would signal that we had sufficient sulfur because it's above 0.25%. If we took some extra and went deeper or lower into the plant, the numbers started dropping. So this shows how relatively easy it is to create different outcomes by sampling differently. And this also illustrates how important it is to actually follow the protocols for sample interpretation. We did our own tissue testing in sulfur trials that we did throughout the state of New York a while ago, and confirmed that critical level of 0.25 is pretty good. In our database with 8 sites, it was 0.27. above which we did not get a response to adding more sulfur. Below it, we did get a response. So that's what this slide is showing. The lower the relative yield, the bigger the response to adding sulfur. There was one site that did not respond to sulfur addition, yet it had a critical level of, it had a sulfur level of 0.2%. That site did not respond because the pH was way too low for alfalfa, and that interfered with its ability to grow better. So one thing that was important in all these studies was that we need to do proper pH management before sulfur addition can work properly. Soil testing is another thing that some folks are promoting for sulfur growth, for sulfur management, for crop growth. There are 6 different methodologies out there that are promoted by different laboratories or programs over the years. And some of those are quite old. Some of them are more recent, but none of them is really, really recent. The most recent one listed here is 1990. When we started looking at sulfur soil testing, we looked at all 6 of those methodologies. And we had to conclude out of the research we did there that the only one that was actually meaningful was the calcium chloride extraction. None of the others gave us results that we could connect to sulfur deficiencies or crop response. Show you 2 slides or two images to show that. Here's the 6 methodologies: Morgan, Mehlich 3, potassium phosphate, ammonium acetate, calcium chloride, and calcium phosphate. These are incubation studies. So what we did here was take soil, add sulfur to it in different amounts, which is on the x-axis. And then we extracted those soils and looked at how much was extracted with those soils. What you want to see in these is that with addition of sulfur, your sulfur concentration in the soil goes up. And that was the case with 5 of the 6 methodologies. Calcium phosphate was showing all sorts of strange patterns here. Tendency to go up with lots of variability. So said, okay, now that is not working. Cross that one off. What we also want to see is that with 4 different soils, our lines follow the same trend, the same slope. And we saw that with potassium phosphate, they're all sort of aligning together. You see that with ammonium acetate, they're different from soil to soil, but the slope is the same. Calcium chloride was right on top for all 4 soils. The Morgan and the Mehlich did not do that. They started separating out the soils. And that's a problem, because then you have to have soil-specific recommendations, which did not make much sense. So we concluded that there were 3 methodologies: potassium phosphate, ammonium acetate, and calcium chloride, that could be potential candidates. But then we also looked at how do these different methodologies in the lab compare to each other. The lab can run soil, extract soil for sulfur, and then analyze by ICP or by a spectrophotometer. 2 pieces of equipment that are different. If we look at the comparison here, you'll see that for all 5 of the 6 of the methodologies, the comparison is pretty lousy. These numbers did not line up between those 2 pieces of equipment. And that's a problem also. So we wanted to be able to have the sulfur with ICP, the photospectrophotometer, and have a straight line, and the only one of these 6 extracts that did that was calcium chloride. So that's the reason why, going back, we say calcium chloride is the only usable test for us here. Not the Morgan numbers, not the Mehlich 3 numbers, and definitely not any of the others in this list. So we did some field testing with these strands of the calcium chloride extraction, and determined a critical level of about 8 ppm. Once again here, if your pH is too low, it messes up everything. So the core responsible action here would be to first manage pH and then manage sulfur. but the critical value of 8 ppm was a very reasonable value. It's been validated in other studies. It was a good way for us to go. This is all research that focused on critical levels for sulfur. We did one more thing on the soil testing side, and that was shown here. Calcium chloride is like a weak salt. It's like a salt solution. It symbolizes sort of the concentration of salts in a natural soil. We looked at how well calcium chloride is extraction compared to a strontium chloride extraction. And it was a 1-to-1 line. That meant instead of running calcium chloride, we can run strontium chloride. And by using strontium chloride in our extraction, we can now also determine the cation exchange capacity much more accurate than any of the existing methodologies. I will come back to this in the next webinar where we talk about potassium, as we will have a section there on case saturation as well. Wanted to point out the approach here, basically to say calcium chloride or strontium chloride extractable sulfur gives you the same numbers. Both are valid. If you also want to know what the CEC, the cation exchange capacity, is of your soil, use strontium chloride, because then you can take calcium, magnesium, potassium in the strontium chloride extraction and determine your cation exchange capacity reliably across all types of soils. More on that at the next webinar. There is a fact sheet that shows some information on the soil testing side and some extra information on Linear as well. Scan the QR code to get to our fact sheets. Now, we talked about tissue sampling to identify a deficiency. We talked about maybe also having a soil test now for alfalfa to help with identifying deficiencies. The quickest way, though, in terms of convincing yourself that you do have a deficiency in your alfalfa fields or in your hay fields, is to do what I did here in the slide. I have two arrows here that are pointing to areas in this field that are sulfur deficient. Here's one left side of this white stake. Here's one on the right side of this stake. This area is sulfur deficient. And the reason why I know that is because we have two areas to the right and the left, in between 4 flags, where sulfur was added. One was gypsum, the other one was sulfomag. 2 sources of sulfur added here and there and not in the middle. And you can clearly see the color differences. Like these were receiving sulfur, the areas in the middle were not. That's an approach. That's a really simple approach. You want to know if you have a deficiency in alfalfa or grass plots. This approach of take 4 flags, take a cup of gypsum, spread it out within a 10 by 10 area, 10 by 10 foot area, and come back at the next cutting and see if you see anything different. Did you see a color difference? You see a height difference? This is a very illustrative way and a very cheap way to go to convince yourself that you do or do not have a sulfur deficiency. So I wanted to add that as a third methodology: tissue testing, soil testing, and 4 flags and a cup of gypsum. All right. If we identify we have a sulfur deficiency, or it would be good to add sulfur, we have options in terms of fertilizers. Here are some examples of fertilizers that you might have available or might want to tap into. The most common ones I see being used right now would be gypsum to some extent, or ammonium sulfate if nitrogen is also needed. It's a common starter that adds some extra sulfur. The sulfur percentages are listed here. It goes from a low of 18% in calcium sulfate or potassium sulfate up to a high of 26% sulfur in ammonium thiosulfate. It's not that one is better than another, they just have different components. Calcium sulfate adds calcium, sulfamag has magnesium in it as well, and potassium. So it's a matter of pricing things out and figuring out what it is that you want to have added. Sometimes get the question, should I use elemental sulfur? And with that, you have to realize that elemental sulfur is not really water soluble. So it's not directly available like the sulfur is in the 5 fertilizers listed on top. Elemental sulfur needs to be oxidized by soil microbes, turned into sulfate, before it can be taken up by plants. So slower than the other sources. The process also lowers the pH of the soil. You're basically forming sulfuric acid in the process. And that could be a concern on naturally low pH soils. That's the reason why sulfur is also recommended if you have a desire to lower the pH of the soil. We don't deal with that much in field crops, but if you were to grow potatoes or some specific vegetables or flowers, you might be concerned about lowering the pH, and elemental sulfur would be the way to go. In terms of meeting sulfur deficiencies and taking care of that, choose from the top 5 to add your sulfur in a more readily available form. I want to address a couple of myths related to gypsum. So gypsum is a really great source of sulfur. It's calcium sulfate. But there's a couple of myths out there, a couple of items of confusion. This slide, the illustration here is from my webinar from last month. It was a slide to show how we can increase the pH. So if we have naturally acidic soil, or we have an acidic soil, it has H+ and aluminum 3+ on the exchange sites of the soil. If I then add a lime product like calcium carbonate, the calcium will exchange and neutralize the soil itself, and it will push H+, aluminum 3+ into solution together with carbonate. The carbonate does the neutralization step. So the carbonate takes care of the formation of aluminum hydroxide, which is a neutral compound, CO2, and water. That second step, the neutralization, is what makes a product a liming product. It's not the calcium. It is the second neutralization step that does it. And calcium is just replacing aluminum and H+ in the complex on the soils, and that needs to go into solution and then be neutralized to lower the acidity, to increase the pH. Now, gypsum is calcium sulfate. So it has calcium. It will replace H+ and aluminum 3+ on the soil, and then push H+ and aluminum 3+ in solution. So exactly the same as a lime product would. But then we have sulfate, and that's not going to neutralize. This second step cannot happen with gypsum. It's chemically impossible. We're actually forming hydrogen sulfide, so that's not increasing the pH, it might be making it worse. So gypsum is not a liming product. Gypsum is a great source of sulfur. It's a great source of calcium if you need that, but it's not a liming product. There's a second myth about gypsum, and that is that it improves soil quality, that it alleviates compaction. And this is a half-truth or a conditional truth. Gypsum is promoted as soil conditioner. It can renovate saline or sodic soils, salt or sodium saturated soils. Why is that? Because high sodium content results in a level of chemical compaction. So basically collapses the soil structure and makes it chemically collapsed into a compacted layer. You have a lot of sodium, that can happen. Calcium can then be used to displace the sodium and allow the soil to gain its structure back. First step in aggregate formation would be to take out the sodium, replace it with calcium. Right? And gypsum can do that because it has calcium in it. All of that is true. The problem here is that we don't have sodium saturated soils in New York. Gypsum has no effect on physical compacted soils if calcium is adequate. It's not being able to do the compaction that it can do with saline and sodic soils. So yes, soil gypsum can be promoted as a soil conditioner for various situations, but we don't have chemically compacted soils here unless we have greenhouse situations. There it is possible to have chemically compacted soils, but typically in our field crops, we don't have a lot of sodium in our soils. We are not sodium saturated here. So then gypsum is also not helping alleviate any compaction. All right, there's a fact sheet on gypsum also on our fact sheet series. Explains this a little bit more detail, the pros and cons, and again, a great source of sulfur, just not a liming product, and it cannot alleviate chemical compaction. Not alleviate compaction in soils that are not sodium saturated. All right, let's switch over. Talked a little bit about fertilizers. Now we're going to talk about manure as a sulfur source. Manure from a previous webinar contains all of the 17 essential nutrients, primaries, the secondaries, and the micronutrients. That includes sulfur. If we look at the sulfur content, we have some book values here that we can use better to analyze it directly. Laboratories that do manure analysis will not traditionally report sulfur in the analysis unless you ask for it. And obviously that comes with an extra cost, but manure can also be analyzed for sulfur. Getting your own analysis will always be better than book values, but we're showing here some ballpark numbers. So there is a bit of a relationship between S content in liquid manure and nitrogen content. The content of sulfur tends to increase with nitrogen. Liquid dairy manure typically, you can see that here, typical nitrogen, and the sulfur here, between 3 and 5 pounds of sulfur per 1,000 gallons of manure. But not all of that sulfur is going to be plant available. So there's some older research that suggests that we should calculate with a 55% availability factor. This could definitely be a little higher or a little lower. There's definitely room for some research here, but let's assume a 55% release number here, availability number, and a range between 3 and 5 pounds. If I do that calculation, I take a conservative 3 pounds of sulfur per 1,000 gallons of liquid manure, 55% availability. If I apply 9,000 gallons, I will have applied with these book values about 15 pounds of sulfur. Remember crop removal of our crops? 15 pounds was about the max for most of our regular yields, possibly up to 30 if we have a really high alfalfa yield. So a 9,000 gallon of manure application will already meet crop removal, independent of what the soil is also going to supply, and a little bit that we still get from deposition from the air also. So plenty, most rates of 5,000 or a little higher will supply more sulfur than the crop will need. So manure, great source of sulfur. If manure is applied, you will not have to worry about a sulfur deficiency. Our field trials, this was in Aurora for growing a crop, 5 years of adding manure and compost under the corn ears, and then stopping with that application under alfalfa years showed that we can quickly lose that sulfur supply that we build up. Here's the 8 ppm critical level. Started out around 12, took 5 years with high rates of compost to build it up to around 19 ppm. And within 2 years, after 2 years, we were back to beginning levels. So manure will benefit soil sulfur for about 1 to 2 years only. If you don't apply manure for 2 years, those fields might become sulfur deficient. All right, so rapid decline in the first couple of years after you stop applying manure or compost. There is a fact sheet on sulfur in liquid manure on our website as well, fact sheet 120, that shows you some calculations here as well. Do we have deficiencies in New York? I mentioned my predecessors did trials back in the 80s with alfalfa trying to figure out if there were sulfur deficiencies, and he concluded there weren't. What about us here now? We did an assessment of 45 alfalfa fields some time ago, and out of those 45 fields, 16% had tissue sulfur at or below the 0.25% cutoff. 44% had sulfur soil test of 8 ppm or less, which signals that maybe not all fields are sulfur deficient yet, but are on their way to become sulfur deficient. So more fields will become deficient in future years. We really should be monitoring and experimenting, and by experimenting I mean 4 flax and a couple of gypsum. So we definitely have deficiencies in New York State for sulfur, and it should be on the list of nutrients that we now actively need to manage. What about soybeans? Several years ago, Jody Latham with CCE did a master's degree on sulfur for soybeans. She did on-farm trials, fully replicated 13 locations in Western New York, 2 sources of sulfur, and comparison with a no sulfur control. And the results of those showed no yield response to sulfur addition, no response in tissue as sulfur, no impact on grain crude protein, and the N/S ratios in the soybeans were sufficient as well. So these trials did not show a response to sulfur. Now remember, the uptake of sulfur for soybeans is a lot less than for alfalfa. It hasn't shown up as a deficiency in these 13 trials. But when we look at partial balances for these fields, negative partial balances, when we don't add any sulfur to these plots and we keep harvesting, here's an example of one of those sites, those negative partial balances indicate that we should start monitoring our soybean fields as well for sulfur deficiencies, because that could definitely start showing. So those trials conducted 2017, 2019 did not show a need to supply sulfur, but I would definitely recommend being vigilant for soybean fields as well, because it's also a legume. But keep in mind that crop removal sulfur levels for alfalfa are much bigger. That's the crop that we need to be concerned about, definitely. And soybean would be the next one. Here's a fact sheet on importance of sulfur for soybeans on our website as well, based on Jody's work in her master's thesis. With that, I am reaching the end. Bit of a wrap up. Legume fields can be sulfur deficient. Most likely sites are coarse textured low organic matter sites. So if the soil doesn't have a lot of organic matter or organic material that could be mineralized, it will also not have a lot of sulfur supply. Coarse textures means it's the sandy soils. Sandy soils have a much better chance of losing sulfur through leaching. So those are also more likely to be sulfur deficient. We have tissue testing as a tool to confirm deficiencies with different sampling methods and timings and different cutoffs. We also have evaluated different soil test approaches, none of which work, with the exception of this calcium or strontium chloride extractable sulfur with a critical value of 8 ppm. And that work was done in alfalfa. So that's a cutoff for alfalfa. If manure is applied in the past year, sulfur deficiencies should not be a concern. If it's been more than 2 years since the last manure application went on and the soil is coarse textured, low in organic matter, you could have deficiencies. And sulfur is almost as mobile as nitrogen is. We need it in sulfate form that can be leached. So we cannot apply sulfur and keep it around for multiple years. You want to do small annual applications. For most crops, 25 pounds of sulfur will be plenty, rather than large multi-year applications, because sulfate does not carry over into future years. And then the final take-home message: test your fields for flax and a cup of gypsum, especially for our crops that we can look over. So hay crops, alfalfa, soybeans also. For corn, it's a little more tricky because by the time you harvest, you can't see that so easily anymore. But this is a really quick and easy way to figure out if there's a need to manage for sulfur in the future. With gypsum, calcium sulfate, great source of sulfur, not a liming product, and it will not alleviate compaction if it's not a sodium saturated soil. With that, one last fact sheet on our list: sulfur for field crops. This is the more general sulfur cycle and crop uptake numbers. And a reference to all our fact sheets that we went through here today on our fact sheets webpage, and find all 5 of them there. I want to end with thanking our funders, participators who have contributed to the various field trials and the laboratory studies, and the greenhouse studies and incubation studies that led to our current sulfur guidelines over the years. And share with you that the potassium management webinar will be on July 10th, not on the 3rd, so the 2nd Friday of the month in July.